So let's look at this problem. In the probability space minus a half-half, together with the Borel sigma field and Lebesgue measure, let us try and find the expected value of random variable x with respect to sigma field G, where x of omega is omega for all scenarios omega, and G is a sigma field that consists of the Borel sets that are symmetric around 0. Now, to find this random variable, conditional expectation, we need to check two properties. The first property is that this random variable expected value of x conditional on G must be measurable with respect to G. The second property, we need to check that the expected value of x times the indicator of any set A must be equal to expected value of the conditional expected value of x given G times the indicator function of A for all A in G. And once we've found a candidate that satisfies both of these properties, then we know that that must be the conditional expectation, because these two properties define conditional expectation uniquely. Now, we've covered symmetric sigma fields in this module a couple of times before now, and we've seen that the functions that are measurable with respect to sigma fields like this tend to be the functions that are Borel measurable and they have the same symmetry as the sets in the sigma field, and in this case the symmetry is around 0, so our expected value must, conditional expectation must be even. In other words, expected value x given G omega must be equal to expected value of x given G applied to minus omega for omega in our sample space. And I'm going to mark this as my first requirement, and I'm going to draw a box around it. Now the second requirement, of course, is exactly the same as saying that the integral over any set A of x dm is equal to the integral over the same set expected value of x conditional on G dm for all A and G. It's really up to you which requirement you want to use. They are completely equivalent. Now, one thing to notice here is that this requirement involves two integrals. The integral on the left hand side is an integral of a function that you already know over the sets, the events in G. So these events are symmetric. On the right hand side is something that we don't know. So it tends to be easier, but it's not always the case, but it tends to be easier to just start with the left hand side. So let's have a look. Let us fix any event A in G. Then if we look at the integral over the set A of x dm, then we can split this into two integrals over two sets, two disjoint sets. So this is the integral of the part of A that's to the left of the origin, so minus a half 0 x dm, plus the integral over the part of A that sits on the right hand side of the origin, x dm. Now the reason why I've split it like this is because, of course, we know that A is equal to minus A, so this is exactly the same as the part of minus A that sits to the left of the origin, x dm, and this integral just stays the same for now. And the important thing to notice here is that this set is exactly a mirror image of this set. The only difference between these two sets is that at the point 0, might be included on the right hand side, but it is not included on the left hand side. This doesn't really matter because we are dealing with a collection of Borel sets and we're dealing with Lebesgue measure most importantly, and the Lebesgue measure of a single point is 0. So actually these integrals, the value of them are exactly the same whether we include this point or not, particularly because x is continuous. So what we can now do is you can notice that if you look at x of omega, x of minus omega is just going to be minus omega, which is equal to minus x of omega. So if we integrate this, the Lebesgue measure doesn't really care whether we're taking the measure of this set or minus this set, it just measures the length. So you can write this integral as the integral over minus this set, which is a intersection 0 1/2 of minus x dm plus the integral a intersection 0 1/2 x dm. And what you notice here is there's a minus here which can go outside. We have minus an integral plus an integral. These integrals are exactly the same except they differ in this one point, but it doesn't matter because x is a continuous function, and we get minus this integral plus this integral equal to 0. And this is the second property. The integral a x dm is equal to 0 for all a in g. Call this property double star. And at this moment, it's really up to you how you want to proceed. You can either try to do some further derivations to get a nice formula for the condition. Of course, what I wrote here was a mistake. What I really wanted to derive is the fact that the conditional expectation integrated over the set is equal to 0. So I'm just going to correct this. Integral over a, expected value of x, conditional on g dm is equal to 0 for all a in g. So this is going to be my requirement. And if you look at these two together, you can do some further derivations if you like, or you can just start to guess and see whether your guess is a good one. Now, looking at this, if I take the integral over all sets A, then my integral of this random variable is equal to 0, which is kind of interesting. Often, when you have integrals, if you have a random variable and all the integrals of this random variable are 0, a good guess is to guess that this guy is 0 as well. So let's guess expected value of x given g of omega is equal to 0 for all for all omega in the interval minus a half. Does it satisfy 2? Yes, it does, because the integral of 0 is always 0. Does it satisfy 1 star? Yes, it does, because the left hand side, under this definition, the left hand side is 0 and the right hand side is 0. So this satisfies star and double star. Therefore, the conditional expectation of x given g is a constant, and in fact it is 0.